Hi boys and girls, this is lecture 1.7 in Unit 1. The topic, radical expressions. Nth roots. This is something we mentioned briefly in the previous lecture, but we're going to expound upon the topic a bit more here. The concept of a square root can be extended to other types of roots. In general, if b to the n equals a, then b is an nth root of a. An nth root of a is written this way, and this reads nth root of a, where n is the index of the radical. This statement here, 2 cubed equals 8, yields this inverse relationship, the cube root of a is equal to 2. Now I just want to point out that if you see a square root symbol and there's no number written there, whatever's underneath here, then the default index is 2. Otherwise, for any other type of root, there would need to be a number there. We're also going to talk about rational exponents in this lecture. You can also write the nth root of a as a power of a. The expression the nth root of a can be written as a to the 1 over n. And in general, the nth root of a to the m can be written as a to the m over n. So now we have fractional exponents. When you see an expression that has an exponent that's a fraction, that means that it's really a radical expression. Let's look at a couple of examples. The square root of 9, again, notice no index written here, so we know it's the default. Default 2 can be written as 9 to the 1/2 power. Where did the 1/2 come from? Since this is 9 to the 1 power and it's a square root, the 1 becomes the numerator of the fraction, the 2 becomes the denominator of the fraction. 9 to the 1/2 means the same thing as the square root of 9, and of course in both cases that simplifies to 3. The cubed root of 8 squared is equal to 8 to the 2/3. Again, the inside exponent becomes the numerator of the fraction, the index of the radical becomes the denominator of the fraction. Now this could be simplified two ways. You could square 8, 64, then take the cubed root and get 4, or you could do the operations in this order, the cubed root of 8 and then square it. Generally this is an easier way because notice it takes you to a smaller number, 2 squared, which is 4. But either operation first will yield the same answer. Here we see a familiar list, the properties of exponents, but what we discover is that the properties of integer exponents can also be applied to rational exponents. So now that we have exponents that are fractions, we need to know how they behave. Well, fortunately, they behave in the same way that exponents always behave. Let's look at a couple of examples. When you have two expressions multiplied together and they have the same base, the rule says add the exponents. Therefore, we can do the same thing here. These two expressions have the same base, so we can say this is 5 to the 1/2 plus 3/2. Adding those exponents gives you 4/2, which of course is 2, and 5 squared is 25. This rule says that if you have an expression raised to a power and then another power, you multiply those exponents. The same thing occurs when the exponents are fractions. So we can rewrite this as 3 to the 5/2 times 2. Of course, 5/2 times 2 is 5, so this simplifies to 3 to the 5th power. Not sure what that is, so we'll leave it like that. This property says that if you have a product raised to an exponent, that each factor can be raised to that exponent. So that's what we're going to do here. Take this lurking exponent and apply it to both of these factors. This becomes 16 to the 1/2 power times 9 to the 1/2 power. Remember, to the 1/2 power means square root of 16 times square root of 9. So that's 4 times 3, which is 12. This property says that if you have a negative exponent, that quantity should be placed in the denominator of the fraction. Similarly, with rational exponents, I'm going to rewrite this now as 1 over 36 to the positive 1/2 power. Now, of course, something to the 1/2 power means the square root of that number, so this is really 1 over the square root of 36, which is 1 over 6. We also have a property that says when you have a fraction and the bases are the same, you can subtract the exponents. So that's what we're going to do here. We're going to let this be 4 to the 5/2 minus 1/2. Of course, 5/2 minus 1/2, 4/2 is 2. 4 squared is 16. And here's the last property. A fraction raised to an exponent says that we can apply that exponent to both the numerator and denominator of the fraction. So that's what we're going to do here and here. This is going to become 27 to the 1/3 power over 64 to the 1/3 power. Now we need to remember that what this actually means is the cubed root of 27 over the cubed root of 64. So this reduces to 3/4. All right, let's practice these properties on a few examples. Starting with these first four, evaluate the following without using a calculator. In other words, we're going to show that we know what these fractional exponents mean. This is really saying the cubed root of -125. Well, the cubed root of -125 is asking what number multiplied by itself 3 times gives you -125, and of course that's -5. 8 to the 5/3, we can rewrite this as the cubed root of 8, and then I'm going to do that operation first and then raise it to the 5th power. The cubed root of 8 is 2 to the 5th power, 32. The 4th root of 81 is asking what number multiplied by itself 4 times to give you 81, and of course that is 3. And then notice we have a couple of things going on here. I'm going to go ahead and take the cubed root of -27, which is what number multiplied by itself 3 times gives you -27. It turns out that that's a -3 to the -2. The negative exponent means this quantity would really prefer to be in the denominator with a positive exponent. Now it's 1 over quantity -3 squared, which gives you 1/9. Now let's do some expressions that have some variables. The cubed root of 250, well, we would need numbers that are perfect cubes. What are those numbers? 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, 4 times 4 times 4, 5 times 5 times 5, 6 times 6 times 6. 250 is not on my list, but 125 is a factor of 250. So I'm going to break this into the cubed root of 125 times the cubed root of 2. I've separated 250 into a factor that will work with the cubed root radical and the leftover factor. So this simplifies to 5 cubed root of 2. Now over here we have this lurking exponent applied to a product. Let's multiply that exponent times the exponents that are currently existing. This gives me 4 times -1/4 is -1, 3 to the -1 times 5 to the -1. Well, of course these exponents actually mean that these quantities would prefer to be in the denominator. That's going to be 1 over 3 to the 1 times 1 over 5 to the 1. I can write that as 1 over 3 times 5, which is 1 over 15. Over here, once again, the lurking exponent can be distributed to each of the factors. This gives me a 25 to the 1/2. 10 times 1/2 is 5, so this becomes a to the 5th, and 16 times 1/2 is 8, b to the 8th. 25 to the 1/2 is the square root of 25, so our final simplified answer, 5a to the 5th, b to the 8th. And over here we have a fraction that needs to be simplified with a square root. Let's go ahead and rewrite this first of all, canceling this x with the 5 that are in the numerator, and that now gives us, as I separate this into 2 radicals, 18 x to the 4th y to the 4th over the square root of 49 z cubed. Now let me go ahead and simplify what I can. It turns out that 18 will break down into 9 times 2, the square root of 9 times the square root of 2. And since this index is a 2, it divides evenly into 4 both times, meaning that all of these x's and y's come out. So this is going to be a 3x squared y squared on the outside of the numerator radical, and left over inside is just this factor 2, which did not simplify. 2 into 4 goes twice, 2 into 4 goes twice. In the denominator, I can go ahead and take the square root of 49, which is 7, and I'm left with the square root of z cubed. Now, to be honest, I'm not allowed to leave that radical there. If only this exponent was evenly divisible by 2, which is the index. Well, let me do what I can to make that happen. What if I multiply the top and bottom of this fraction by z to the 1 over z to the 1? Since 3 plus 1 is 4, that would give me z to the 4th power in the denominator. Let's move down here. In the numerator now, I have 3x squared, y squared, and now this 2 times z under the radical. And then in the denominator, the 7 is completely out, and we have now created this situation, z to the 4th under the radical, which is awesome because 2 goes into 4 evenly, meaning our final simplified answer will be 3x squared, y squared, the square root of 2z in the numerator over 7z squared. Now remember that inside numbers and outside numbers don't mix. So if you're tempted to do any canceling with these z's, do not do so. Under the radical, outside the radical, so no simplification can take place. This is as far as you can go with this problem. Now let's do a few examples where we're utilizing operations with variable expressions containing radicals and rational exponents. For letter A, we're asked to multiply two radical expressions together. Well, a couple of things to remember. If you're going to multiply radical expressions together, the indices need to match, and they do here. Another thing to remember is the outside numbers can be multiplied together, the inside numbers can be multiplied together, but outside and inside don't mix. You would never be multiplying this 3 times this 5 or this 32 times this -6. So let's do what we can. First of all, 3 times a -6 gives us a -18. And then a 4th root radical. 32 times 5 is 160. Of course, we pause and see if possibly we can simplify further. We do have a 4th root radical, so we need to look at 4th powered numbers. 1 times 1 times 1 times 1, 2 times 2 times 2 times 2, 3 times 3 times 3 times 3, 4 times 4 times 4 times 4 is 256, etc. Now you can see that 160 is not on the list, but 16 is a factor of 160, and it is on the list. So of course the -18 is just outside weighting. If anything comes out, it will be multiplied by that -18. And now we're going to break down 160 into the 4th root of 16 times the 4th root of 10, 16 times 10. This will work with the 4th root index. This will be left over. The 4th root of 16 is 2 times -18 ends up being -36, and then the 4th root of 10. And that's your simplified answer. Look at letter B. Now we're being asked to subtract. And of course, as with any expression, we need them to be like terms. These do not look like terms, even though the indices are the same. But looks can be deceiving. Let's simplify both of these expressions first and see if possibly they are like terms in disguise. Well, we're going to need perfect cubes. 1 times 1 times 1, 2 times 2 times 2, etc. And let me just put a few up here. You can see that 48 is not on the list, but 8 divides evenly into 48. So let's simplify the cubed root of 48. The 5 is outside weighting, and then of course 48 breaks into the cubed root of 8 times the cubed root of 6. Let's look at 750. Again, it's not on the list, but 125 goes into it. So this is minus, and now this breaks down into the cubed root of 125 times the cubed root of 6. The cubed root of 8 is 2. Multiplying that by the 5 that's already out there gives us a 10. Cubed root of 6. The cubed root of 125 is 5, and of course that's minus 5 cubed root of 6. Well, look at what we have here, like terms. Now that the radical portion is exactly the same, they are like terms, and we can subtract 10 and 5 and get 5 cubed root of 6. Over here, this is a problem where it's going to be easier to do this if we rewrite this using fraction exponents, rational exponents. X to the 2/3 times x to the 4/6, which as you can see is also 2/3, but we'll just leave it like that for now, to the -3 lurking exponent, which can multiply by both of the currently existing ones. -3 times 2/3 gives us -2, and again -3 times 4/6 is also going to result in a -2. -12/6 is -2. We can add these exponents together since the bases are the same. -2 plus -2 is -4. And of course that negative exponent is expressing the fact that this quantity would actually prefer to be in the denominator with a positive exponent. And so that is your simplified answer. For letter D, we have to deal with the fact that there's a radical in the denominator. If only 5 divided evenly into 6. Even though 5 goes into 6, it doesn't go in evenly. So rather than simplify and then deal with the leftover, I'm just going to go ahead and multiply by the 5th root of x to the 4th over the 5th root of x to the 4th. 4 more x's added to the 6 that we have will give us 10. Of course, in the numerator, that gives us 3 5th root of x to the 4th. That radical will be in the numerator, but we don't really mind if a radical is in the numerator. But in the denominator, this is the situation I have created. This is now x to the 10th. Fortunately, 5 goes evenly into 10. That gives me an x squared in the denominator and a -3 5th root of x to the 4th in the numerator. Of course, no canceling here. Inside numbers, outside numbers do not mix. Now we're going to switch gears a little bit and talk about operations with functions and composition of functions. Given these two functions, let's perform the indicated operations. You can add them, subtract them, multiply or divide them. I'm just going to subtract and then multiply. And then in C and D, we'll talk about composing the functions, which is basically inserting one function into the other and simplifying. First with subtracting, it's exactly what you think it is. This function, f of x, minus this function, g of x. So let's write that down. 3x squared minus 5x plus 1 minus, now be careful here, because we know this is a very common careless error. It's certainly not a bad idea to distribute the negative so that we have the signs right in this second parentheses. This becomes 3x squared minus 5x plus 1 plus 3x minus 4. There are no like terms with the 3x squared, but we can add the -5x and 3x and get a -2x. The 1 and -4 now give us a -3, and that is f of x minus g of x. Now let's multiply f of x times g of x. That means we're going to take the trinomial 3x squared minus 5x plus 1 and multiply it by the binomial -3x plus 4. Since we're multiplying a 3 by a 2, there will be 6 initial multiplications since every term in the trinomial has to be multiplied by every term in the binomial. So 3x squared times -3x is -9x cubed. 3x squared times a positive 4 is positive 12x squared. That's the first round of multiplications. Now moving to -5x times -3x, a positive 15x squared, and then -5x times 4, -20x. The last round of multiplications with positive 1 times -3x, -3x, and 1 times 4 is 4. 1, 2, 3, 4, 5, 6. You can check to make sure you haven't missed anything by counting. And now let's look for like terms. -9x cubed doesn't have any like terms, but 12x squared and 15x squared are like and become 27x squared. -20x and -3x are like and become -23x, and then plus 4. Now for compositions, notice that f is listed first for letter C. That means g of x will be inserted into the f function. So this whole piece right here will go into this function wherever there's a variable currently existing. So let's rewrite the f function, but wherever there's an x, replace it with -3x plus 4. So that's going to be 3 rather than x squared. It's going to be -3x plus 4 quantities squared. Minus 5 rather than x, of course, -3x plus 4, and then plus 1. Now that you've inserted the g of x function in, we simply will have to simplify. Negative 3x plus 4 quantity squared means we'll FOIL this, and I'll do that foiling up here. Negative 3x times negative 3x is positive 9x squared. Negative 3x times 4 is negative 12x twice, negative 24x, and then 4 times 4, 16. Now let's distribute the 3 and distribute the negative 5 here. We end up with a 27x squared minus 72x plus 48. Then the negative 5 times the negative 3 is a positive 15x, and then minus 20 plus 1. There are no like terms with 20x squared, 27x squared, but negative 72x and positive 15x gives us a negative 57x. 48 minus 20 is 28, and then plus 1 is 29, and that is your simplified answer. Now let's do the same thing but in reverse. G is listed first, so we're going to take the f of x function and insert it in for x in the other function. So it's going to be negative 3x plus 4, but where the x is, we insert the other function. 3x squared minus 5x plus 1, and then of course plus 4. This one's a little bit easier to simplify. Distributing the negative 3 gives me 9x squared, then plus 15x minus 3 plus 4. Only these like terms, negative 9x squared plus 15x plus 1, and that is your simplified answer. Our next topic, inverse functions. Inverse functions interchange input and output values. Because of this, the graphs of inverse functions are reflections of each other about the line y equals x. All right, how do you create an inverse function? Here are the steps. Replace f of x with y, then switch x and y, then solve for y, and then replace y with f inverse of x. That's what this notation means. So let's do that with this example. We start with f of x is equal to x cubed minus 2. First, replace f of x with y, and then switch x and y. Notice in doing so that y is no longer isolated, it's embedded in the function. Isolating y again will create the inverse function. Let's add 2 to both sides. This gives us x plus 2 equals y cubed, and then the cubed root of both sides gives us y is equal to the inverse function cubed root of x plus 2. And for our final step, we'll replace y with f inverse x, which indicates that this function is the inverse of the original one that we started with, the cubed root of x plus 2. Now let's graph both the original function and the inverse function to see the symmetry about the line y equals x that was discussed in the definition. Starting with x f of x, the original function, we'll just use the ordered pairs negative 2, negative 1, 0, 1, 2, and when we plug negative 2 in for x, negative 2 cubed is negative 8 minus 2, negative 10. Negative 1 cubed, negative 1 minus 2, negative 3. 0 gives us negative 2, 1, negative 1, and 2 cubed minus 2 is 6. Let's graph this. Negative 2, negative 10 is down here somewhere, negative 1, negative 3, 0, negative 2, 1, negative 1, 2, 6 is up here. And so here is the curve that the original function represents. Now let's graph the inverse function. Since it's a radical, I'm going to try to put numbers in for x, which will make this perfect cubes. I'll start with the cubed root of negative 8. To make that a negative 8, x will need to be negative 10. Negative 10 plus 2, negative 8, the cubed root is negative 2. Look at that. It's exactly the opposite of that ordered pair there. That's amazing. The next perfect cube is negative 1. So if I let x be negative 3, negative 3 plus 2 is negative 1, the cubed root of which is negative 1. Then let's let this be 0 by letting x be negative 2. Of course, that gives me a 0. And then I want to make this a positive 1, so I'll need to let x equal negative 1. The cubed root of 1 is 1. And then I want this to be an 8, so I'm going to let x be 6. And the cube root of 8, of course, is 2. It's interesting how those ordered pairs are exactly the opposite of each other. Now, negative 10 is way out here, negative 2, something like that. But then we have negative 3, negative 1, negative 2, 0, negative 1, 1, and then 6, comma 2. So here is this curve. Now we are told that this is going to be symmetric about this line, the line y equals x, which goes through the third and first quadrants and through the origin at a 45-degree angle. And of course you see that beautiful symmetry represented right there. Let's take a few moments to discuss the graphs of the square root and the cube root functions. Here is the parent function of the square root function. F of x equals the square root of x. You can see that it starts at 0, 0. It has a distinctive domain because since under the radical you can have no negative numbers, it's one of the few functions that has a distinct starting place, as this does. The cubed root function, the parent function, is g of x equals the cubed root of x because under an odd index radical you can have negative numbers, then the domain is all real numbers and the range is all real numbers as well. It's only when the index is even that you need to worry about negative numbers under the radical. So this is what the parent function of the square root function and the parent function of the cubed root function look like. Let's graph one of them with various transformations. It's a square root, and you can see that there's going to be a horizontal shift, a vertical shift, a reflection, and even a little bit of a dilation as well. Now, as I choose x values, I'm going to choose things that keep these numbers under here perfect squares. Let's start with making this a 0 by letting x equal 3. 3 minus 3, 0, square root of 0, 0 plus 2 is 2. Oops, I was about to put a positive 2 there, but let's just let it be a 2. The first perfect square after 0 is a 1. I can let this become a 1 by letting x equal 4. 4 minus 3 is 1. The square root of 1 is 1 times negative 2 is negative 2 plus 2 is 0. The next square root is 4. So let's let x be 7. Now, if you were doing this on your calculator, you could certainly get some decimals and graph them, etc. But I like choosing x values that are going to make some nice, neat integers to deal with. 7 minus 3 is 4. The square root of 4 is 2 times negative 2, negative 4, plus 2 is negative 2. The next perfect square is going to be 9, so let's let x be 12, because 12 minus 3 is 9. The square root of 9 is 3 times negative 2, negative 6, plus 2 is negative 4. And let's plot these points. 3, comma 2 is our first point. And now if you think about it, you can't have anything to the left of 3 because if you put 2 in here, that gives you a negative number under the radical. It's a square root function, so there's a distinctive starting point for the domain, and that's going to be 3, comma 2. 3 on the x-axis and 2 on the y-axis. Now if we graph 4, comma 0, we get this. 7, comma negative 2, and 12, comma negative 4 takes us down to here. And so here is the reflected, dilated, horizontally and vertically shifted parent function square root of x, and that's what it looks like there. Now this is 3, comma 2, and it's going to give us the clue as to what our domain and range is. The domain, x values that are greater than or equal to 3. The range, y values that are less than or equal to 2. Less than rather than greater than because it's a reflection. And that is how you graph these types of root functions. Our last topic for this lecture is solving radical equations. Now we have an equal sign, which means we have an equation, and of course an x value to discover, possibly more than one. How do we solve radical equations? Isolate the radical on one side of the equation if necessary, raise each side of the equation to the same power to eliminate the radical and obtain a linear, quadratic, or other polynomial equation, and then solve the polynomial equation using techniques learned previously. Check your solution, as you may get extraneous solutions. Now, starting with this example, this is not technically a radical equation because there's no radical involved. But as we know, an expression raised to a fractional exponent means it is a radical. So we're going to follow these steps. We're going to isolate the radical expression on one side, giving us x plus 2 to the 3/4 power is equal to 8. Now, instead of raising it to the same power as the index of the radical, for this situation, we're going to eliminate the index and the exponent all at once by raising it to the reciprocal power of that fraction. Why the reciprocal? 3/4 times 4/3 is 1. So, when we do this to both sides of the equation, these guys multiply together, give us x plus 2 to the 1, which of course is just x plus 2. Now, 8 to the 4/3, when you take the cubed root of 8, you get 2, and raise it to the 4th power, you get 16. Now to solve, when you subtract 2 from both sides, you get 14. Remember, it's a good idea to check your answers. So 14 plus 2 is 16. The 4th root of 16 is 2. Cubed 8 minus 1 is 7. This checks out. Over here, we do have the radical expression isolated on one side, and we are going to square both sides to release the 7x plus 15 from the radical. But of course, squaring the left side of the equation means we're going to need to FOIL. X plus 1 times x plus 1 is x squared plus 2x plus 1. Be careful that you don't just say x squared plus 1. It has to be written down twice and FOILed to get the correct answer, equals 7x plus 15. Since the square root and raising to the squared exponent are inverse operations of each other, they cancel each other out, and the expression inside just drops out, and that's what we wanted to happen. So now let's move everything over to the, let's move everything over, start that again. To the left side of the equation, since we have a quadratic, we're going to need to get everything over there on one side and 0 on the right side. Nope, we're having a little trouble with this one, little technical difficulties, but we'll get there. Subtract 7x and then subtract 15. On the right side, 0, which is what we wanted, and then x squared minus 5x minus 14, which, thank goodness, factors quite nicely into x minus 7x plus 2. Giving us two potential answers. Remember potential because we're going to check to make sure that nothing is extraneous here. So we get x equals 7 and x equals negative 2. Let's try 7. 7 plus 1 is 8, of course. 7 times 7 is 49, plus 15, 64. The square root of 64 is also 8, so 7 checks out as a valid answer. Negative 2 plus 1 is negative 1 on the left, and then 7 times negative 2, negative 14 plus 15 is 1, positive 1 on the right. Negative 2, therefore, is extraneous, yielding only one solution to the quadratic. That's it for today's lecture, boys and girls. And now that you have learned that square root and squaring are inverse operations of each other, you'll be able to decipher this message. God bless you.